Hello, everybody out there in pre-calculus world. This is Mr. Gallagher, and I hope your distance learning is going well. Today, we are going to cover section 6.4, which is partial fraction decomposition. And one reason we're covering this topic is because when you get to calculus, you're going to be talking about things like area under a curve or under a graph. And one of the techniques used to find this is going to be taking rational expressions and decomposing them down into simpler rational expressions. So we're going to learn some of the basics of that today that you're going to cover and take with you into calculus next year as well. So before we get into that, though, I want to talk about just adding some, how fractions are added together first, just as an example. Let me give you a quick recap here of something you learned back in elementary school, right? So if you remember, if you had the fractions like 2/3 and you were going to add the fraction 3/5 together, right? What would you do? Well, you have to find what's called the LCD, the least common denominator, right? And the least common denominator would be, you would take the other denominators and you would take the factors of those and come up with a denominator that represented all the factors, but in the least possible form. So the factors of 3 and 5 together are going to be 3 times 5, right? So it's 15, but I'm just going to write it as 3 times 5 right now. And then I have to rewrite the numerators by changing the numerators by however I change the denominators, right? So this first fraction, that was 2/3, looks like I multiplied the denominator by 5 to get to 15. So now 2 is going to get multiplied by 5, right? And then for the second numerator, I had a 3, and it looks like the 5 on the bottom got multiplied by 3, so this is going to get multiplied by 3, right? So as a result, we're going to get 10/15 plus 9/15, and that's going to be 19/15 as our answer. So that's just kind of a recap of how we add fractions together using least common denominators. What we're going to do today, as I said, we are covering section 6.4, and this is called partial fraction, if I could spell, fraction decomposition. So what we're going to do here is we are going to go backwards. We're going to take a rational expression and we're going to break it down into simpler fractions. Let me give you an example. So this first one, I have the fraction which is x plus 13 over x squared minus x minus 20. Now I'm going to break that down into two simpler fractions. But in order to do that, I need to look at the denominator and look at what factors may have gone in to creating this least common denominator, right? Because my least common denominator is that x squared minus x minus 20. Well, let's break that down. What are the factors of x squared minus x minus 20? Well, if I factor that, that's going to be what? X minus 5 and x plus 4, right? So that's what I'm going to be breaking these fractions down into. Here's two simple. It's like kind of like we had with we had a 3 and a 5 in this other example up here, and we knew that together it was going to be 15. Well, if I broke the 15 down into factors, I knew my factors would have been 3 and 5. So I'm kind of doing that. I'm taking that x squared minus x minus 20 and breaking it down into two factors that are going to make up my two simpler functions, my two simpler fractions. Now, the problem is I don't know what goes on top, right? I know this is going to be some number a, and this is going to be some number b. My goal is to figure out what a and b is. So how do I do that? Well, now let's say if those are my fractions, if I was going to find my least common denominator, let's rewrite those two fractions with the least common denominator. Let me explain. So I've got x plus 13 over x squared minus x minus 20. In order to get that, I have these two fractions up here. The first fraction I'm going to change into x minus 5 times, and I'm going to put an x plus 4 here. And I'm also going to say, well, this is going to be an x plus 4, and I'm going to have to put an x plus 5 here. So now they have the same denominator. Well, when I put this x plus 4 in the denominator here, that means that a is also going to get multiplied times x plus 4, right? And then on this one over here, when I put an x plus 5 in this denominator, that meant that b would have to get multiplied times x plus 5, or sorry, x minus 5. These are x minus 5s. Let me change that right here. X minus 5. So now I've got my two fractions that are rewritten now with least common denominators. Again, remember the original fractions, the ones I'm trying to look for, are these two up here, a over x minus 5 and b over x plus 4. I've now combined them using my least common denominators, and just like I did up here when I had to multiply the 2 times the 5 and the 3 times the 3, I had to multiply the a times x plus 4 and then multiply the b times x minus 5, so I get equivalent fractions. Well, now that I have all of these denominators the same in this entire equation, do you remember when you have fractions that are equal and you have denominators that are all the same, you can ignore the denominators. Like for instance up here, I could ignore in this this equation up here, I can ignore the 15s and I can just look at 10 plus 9 equals 19. Well, now down here, I'm going to say I can ignore the denominators and say x plus 13 is equal to a times x plus 4 plus b times x minus 5, right? And that is an equation that I can solve for. And I'm going to try to solve for a and b. Unfortunately, I have one equation, but let me multiply this out. And I'm going to show you one way of solving this. And there's actually another way too, which we'll look at later. So I have x plus 13 equals, I'm going to multiply this out, ax plus 4a plus bx minus 5b, right? And now if I group the x and the non-x terms together, I have ax plus bx and plus 4a minus 5b. Well, what I can look at, I really know that whatever this happens to be, I know that it's going to have to equal this 1x over here, right? So I know that ax, I'm going to say a plus b times x plus 4a minus 5b. I know that that a plus b right here is going to have to equal 1 over here in order for this to be correct. So one equation I know I have is that a plus b has to equal 1. Likewise, I know that, it was a different color, this 4a minus 5b is going to have to equal 13, right? So I can write that down as well. 4a plus, minus 5b equals 13. Well, now I have two variables, two unknowns. And so I can solve for a and b. And again, that's what I'm trying to look for because remember, again, back up here, my original problem, I'm trying to solve for a and b. So what can I do? How do I do this? Well, I can do substitution. I can do elimination. I'm going to do elimination. I'm going to multiply that entire top equation times 5. And I'm going to get, what, 5a plus 5b is equal to 5. And the reason I did that is because down here I've got 4a minus 5b is equal to 13, right? And through elimination, I can combine those two, and this is going to cancel out, and I'm going to be left with, what, 9a is equal to, what is that, 18 when I add them all up, which means a is equal to 2. Well, if a is equal to 2, I can now substitute that in one of my other equations. I know 2 plus b is equal to 1. Well, that means that b has to equal negative 1. Well, there I solved it. So now my answer is going to be, if I go back to the original problem, which is x plus 13 over x squared minus x minus 20, is going to break down or be decomposed into these two fractions. A, which is 2, so now I have 2 over x minus 5 plus negative 1 over x plus 4. And that is my answer because I've now broken them down into that, broken that original fraction of x plus 13 down into two smaller fractions, 2 over x minus 5 and negative 1 over x plus 4. Let's try another example. And I'm going to show you an easier way of solving this particular example here. So number 2, let's go back to blue. Number 2 is going to be the fraction 2x plus 5 over x squared minus x minus 2. So again, I want to break these down into, well, how many factors am I going to have? Well, again, I'm going to have 2 factors. So my factors are going to be x minus 2 and x plus 1, right? And I'm going to have, again, an a and a b here. So I want to figure out what can I break this down into, what 2 smaller fractions, 2 smaller rational expressions that I can break this original problem down into. Well, if I multiply the a times x plus 1 and multiply the b times x plus 2. So if I break it down a little bit further, in fact, I'll just write the equal sign over here. A times x plus 1, because that's going to be x minus 2 and x plus 1. And then this is going to be x plus 1 and x minus 2. That means b is going to get multiplied times x minus 2, right? So those are equivalent fractions. And because I now have all my denominators the same, right, that's still going to be 2x plus 5 over x squared minus x minus 2, which is x minus 2 times x minus 1. I can now just look at my numerators. And that's going to be this plus b times x minus 2, right? And if I multiply them out, I'm going to get 2x plus 5 is equal to, that's going to be ax plus a plus bx minus 2b. And again, looking at what do I know the x's have to equal, if I group them together, 2x plus 5 is equal to, that's going to say that ax plus bx, and that's going to say plus a minus 2b, right? And if I know by, again, grouping them together, I know the x's have to equal the x term and the constants have to equal the constants term. I know that a plus b is going to have to equal 2. Those are the x's. And I also know that a minus 2b has to equal 5. And again, I can use substitution or linear combination or elimination. I'm going to use elimination. I'm going to multiply this bottom equation times a negative 1. So let's see what I get here. I got a plus b equals 2. And that's going to be minus a plus 2b equals negative 5. When I add those two up together, what do I get? 3b is equal to negative 3, which means b must equal negative 1. And if b equals negative 1, well, then I can use that equation, say a minus 1 equals 2, so a must equal 3. So my answer for the expression 2x plus 5 over x squared minus x minus 2 is going to be equal to, we said a is 3, so 3 over x minus 2 plus negative 1 over x plus 1. And there's my answer. I'm going to actually show you what might be considered an easier way of solving this. I'm going to go back up to this part of the problem right here when I got to this part that the 2x plus 5 equals a times x plus 1 times or plus b times x minus 2. And I'm going to bring that all the way down here. I'm going to rewrite that equation. So that was when I had 2x, let's do it in a different color. So when I had 2x plus 5 is equal to a times x plus 1 and then b x minus 2. Instead of coming up with 2 equations with 2 variables, one thing I could have done is I could have chosen some values for x and see if I could eliminate it and solve for a different value, solve for a or b. For instance, I'm going to put in x equals negative 1. And if I plug in x equals negative 1, look what's going to happen to this term right here. That's going to end up being 0. So I'm going to eliminate my a. So, and I can solve for b. So look what happens when I plug in x equals negative 1, I'm going to get negative 2 plus 5, right? Equals a times 0 plus b times, well, negative 1 and negative 2 is negative 3, right? So I'm going to get 3 is equal to negative 3b, which means what? B has to equal negative 1, which there's a way of getting b equals negative 1. Likewise, when I said 2x plus 5 equals a times x plus 1 plus b times x minus 2, what if I chose x equals 2? What would I have done? If I plugged in x equals 2, well, then I would have got 4 plus plus 9 equals a times 3 plus b times 0. And that would have eliminated this, and I would have had 13 is equal to, not put plus 9. Why did I put plus 9 here? It should have been 5. I was thinking ahead. Sorry. 4 plus 5 is equal to 9, right? That was a 5, not a 9. 9 is equal to 3a, which means a is equal to 3. So that was an easier way of getting my a and b, and I would have got the same answers as I did up here as well. So there's 2 examples of partial fraction decomposition. I have one more example I'm going to show you, but that's going to be in the next video.